conservation laws and collisions, in which we apply momentum and energy principles to 4 types of collisions. Our goal here will be to practice looking at a scenario and identifying whether energy will be conserved and whether momentum will be conserved. So here's a setup for 4 types of collisions. I've got these 3 boxes, say, all sliding around, knocking into each other, and a wall on the left, a left wall with an elastic spring on it, a wall on the right with no spring, the right wall, and box A happens to have an elastic spring attached to it. So a reminder that when we say collision, we mean a brief interaction with large magnitude but short-lived contact forces. What do we mean by large magnitude? Large compared to what? Well, compared to other forces it might be competing with, such as kinetic friction here as the boxes slide on this rough surface. We'll assume here in our collisions that the force of kinetic friction on each box will be much, much less than the magnitude of the contact forces during the collision, such that the impulse exerted on the box by friction is much, much less than the impulse exerted on the boxes by the contact forces. And likewise, such that the work done on the boxes by kinetic friction is much, much less than the work done on the boxes by the contact forces. Graphically, we would mean here that the force of kinetic friction is so small that even though it's constant, that over this short time interval, force versus time, that this area here representing the impulse imparted by that force of kinetic friction, we're assuming that this area, this impulse, is much, much less than this area, this impulse imparted by the contact forces, which is short-lived but very, very large. So that's the approximation we're making here. We'll be able to neglect our forces of friction. The collision is so brief but strong that we may neglect friction with the surface from time 1 to time 2. Okay, so we'll have 4 collisions to look at. The wall with A with B with C, and C with that wall. So number 1, collision between the left wall and box A. So this collision is mediated by this elastic spring here, this ideal spring. We'll look at conservation of momentum and conservation of energy. So we would set up for the momentum of box A that its change in momentum is due to the impulse exerted on it. This is just a single moving object. And we would note that the impulse imparted to the box by the wall would be equal to the change in momentum of box A. So A's momentum will change. Our moment 1 will always be just before the collision starts, and moment 2 will always be after the collision is over. So A's going to come in, hit that spring, and bounce back. And we see that there will be a net force and net impulse imparted on A to the right from the wall. Okay, let's come back to momentum in a moment. Over to energy for a moment here. The change in energy of box A, it's the only moving thing in our system, is due to the work done by non-conservative forces on it. And this elastic force, this spring force exerted by the wall, is of course a conservative force. So there is no work done by non-conservative forces here during our brief collision, during which friction doesn't have time to act. So the conservation of mechanical energy for box A looks like this: the change in kinetic energy plus the change in spring potential. And if our moment 1 is before the spring is compressed, and our moment 2 is after the spring has returned to its original length, then at the very beginning, US is 0, and at the very end, US is 0. So the total change in spring potential energy would be 0, which is then indicating also to us that the change in kinetic energy would be 0. So in this collision, which is clearly elastic, the kinetic energy of A at the beginning is the same as the kinetic energy of A at the end. It's going to bounce off with the same speed at which it came in. So looking back over here, this indicates that if the speed is the same, both before and after, then the momenta before and after are equal but opposite. Recall that momentum is a vector, so if they're equal in magnitude, they are opposite in direction, indicating that the impulse that must be imparted to A by the wall must be equal to the opposite of twice A's initial momentum. Its initial momentum is to the left, the impulse is to the right, and it must be double that magnitude of that initial momentum in order to remove it and then reverse it completely. So in conclusion here, the momentum of A is not conserved in this collision due to that external contact force imparted by the wall, but the energy of the system is conserved. So we would call it an elastic collision because energy was conserved. The momentum didn't get destroyed by the impact. It cannot be destroyed. It was simply transferred to the wall, which is attached to the Earth. So this momentum, this leftward momentum that A had, got transferred via the wall to the whole planet Earth, where it's impossible for us to keep track of it. So we just say that that momentum has left the system. In reality, the entire Earth would have gained some leftward momentum in its orbit around the sun. That's where that momentum goes. It's not destroyed, but we can no longer keep track of it if it gets transferred to the Earth. Okay, so momentum not conserved, energy conserved. Collision number 2. A and B. Here we have two moving objects this time that we can put into a system. So a system of these two moving objects, their momentum can be analyzed like this. The net external impulse on this system will be equal to the change in the total momentum of the system, change in momentum of A plus change in momentum of B, and there is no net external impulse here during that brief collision. So this is 0, indicating that the change in momentum of A in the x direction is equal to the opposite of the change in momentum of B in the x direction. Whatever momentum A loses, B gains, vice versa. So the momentum of the system here would be conserved. No net external impulse. Momentum is conserved in this two-object collision. As for the energy, any change in energy of the system would be due to work done by non-conservative forces. There are no non-conservative forces doing work here because that spring force, that elastic force there, is conservative. So this would be our conservation of energy equation. It would have one term for each kinetic energy, for A and for B, and then one term for the single spring interaction between them. So here, if the spring is not compressed before the collision, then US beforehand is 0. If it's not compressed after the collision, then US afterwards is 0. So the change in US is 0 minus 0. Overall, this is our energy result. Whatever kinetic energy A loses, B gains, and vice versa. Equal and opposite changes in kinetic energy. So the energy of the system is conserved as well. That makes this an elastic collision. So here's one case where both momentum and energy would be conserved. Two-object collision with an elastic interaction between them.